So our goal is to convert this transfer function with a polynomial in the numerator, right? So we have the transfer function. This is the transfer function, and we have polynomial in the numerator. This is the polynomial. Okay. So let me do it. Yeah, this is the thing. So first of all, so if you remember what we did before, we had this kind of diagram, right? So we have R coming in. Let me do it here. We had RS coming in. Then you have, it's too small. Sorry about that. This is RS coming in. So we have 1 over S squared plus 7S plus 9, right? Then once it, so after that, so you have your input is RS. Then here input is X1, right? That's what we did last time. Then we feed this X1 to other block. In this case, what is the block? 2S plus 1. Then comes out CS. Okay, this is just like last time. Okay. Or you can say, did I say X1 or it's simply X? Because there are not many X's, right? So just simply call it X. Okay, so it doesn't matter. All right, so let's talk about the first block first, okay? Let's talk about the first block first, meaning this guy. So how do you handle this guy here, from here to here? What is your transfer function here? If you consider this block only, your transfer function will be output over input, right? Output is XS over input is RS, which is 1 over S squared plus 7S plus 9. That's your, then if you cross multiply, what do you get? You got S squared X plus 7 SXS plus 9 XS equals RS. Now take the inverse Laplace, right? If you take the inverse Laplace transform here, inverse LT, Laplace transform, then what do you get here? This guy gives me little x dot, double dot. Now it's the function of t, right? Plus 7 x dot, function of t, plus 9 x function of t equals little r function of t. Okay. Now it's time to define the state variable, is it? Isn't that right? So define the state variables now. Define state variables. So what is the definition? Your x1 equals x. So x2 equals x dot. Because you have to go all the way to n minus 1, right? Here n equals 2. So n minus 1, which is 1. So we have just n minus 1 here. That's how you define state variable, if you remember. Then how do you write this guy in terms of state variable? So you have x1 dot equals x1, x dot, right? So let's do this one here. Because you need the dot, right? So first order, right? You need the first order here. x1 dot equals x dot. So x dot is x2. So actually I can write x1 dot equals x2 here. This is equation 1. Then what is x2 dot? x2 dot, right? x2 dot. You see here? x2 dot equals x double dot, right? Okay. So, oops, x2 dot, I did double dot here. This is x2 dot equals double dot here. That's what I meant. So x2 dot equals x double dot. So x double dot, what do you get for x double dot from here? Help me here, please. RT on the right. Then how about this guy? This guy goes to the left, right? So minus 7. What is x dot? X dot is?
x2.
X2, thank you. So x2. Then it goes to right. Minus 9. X is x1, right? Okay, that's what it is. Now your two equations are there. So from here, can you figure out x dot? X dot, remember x dot equals, what is the matrix here? Plus, you have some matrix here, plus R, right? That's the x dot matrix. X dot equals, yes, x dot is x, what is this x dot? X dot is x1 double single dot, x2 single dot. That's your x dot. Then you have, oops, I forgot something here. I forgot x here. Plus, so x is x1, x2, right? So what is the matrix here? Help me. So in the first one, you just have x2, meaning you just have x2, you don't have x1. This guy is done. Then in the next one here, you have R, right? Oh, by the way, this R is 0 here, right? And for this next one, you have R, that's why this is 1. R times 1 is R. Then for the x2 part, you have minus 7. For the x1 part, you have minus 9. So that's your thing. Now, how about the C? Remember the C, you have to find the C now from here. This part is done. This part is done. Now we have to do the next part now. So we got this guy already. We take care of this guy. Now given this guy, this is the input to the other guy now. So we have to talk about this guy now. So here, what is your CS? CS equals, help me here please. CS over XS equals 2S plus 1. So what does it give me? This gives me CS equals 2S plus 1 XS. So they take the inverse Laplace. CT equals 2 times X dot T plus XT, right? So we know this is X1, X is X1, right? So this guy is X1. This is X1. How about X1 dot? X dot is X2, right? So 2X2 equals CT. Now this is equation number 3. Based off that, can you write the C? So what I meant is this now. So let's do the, this is one of the equations we have. Oops, sorry. So this is one of the equations. Oops, sorry. This is one of the equations we already have. Now we need to figure out similarly. This is X. Now what is the output equation now? From here, you can find the output equation. So what is the output equation? C equals, so what is the matrix? Then your X is X1, X2, right? X is X1, X2. So here X1 is 1, X2 is 2. So this is my output equation. Guys, any questions so far?
Yeah, I have a question super quick. So in getting equation 3, can you talk a bit, or can you, talk a bit more about how we got to the second part of that, which would be CT equals 2x dot t plus xt?
Yeah, so this is, so you understand this line, right?
Yeah, I understand that line.
Yeah, so what we did, we do the Laplace transform, inverse Laplace.
Oh, okay.
So the CS will be CT, then 2S X will be 2X dot, right?
Mm-hmm.
Then this guy is XT.
Okay.
Makes sense?
Gotcha. Thank you.
All right.
Yep, makes sense to me.
Okay, good. So now let's do the thing. What is the thing? We are talking about the other one. What is the, we are trying to do the block diagram, right? So how do you do the block diagram for this guy? Let's do the block diagram here. Block diagram. Okay. So now we have how many? We have this guy, you know, for the block diagram, you can take this guy here, right? X2 dot, yeah, you can take this guy. You can take this guy, whatever, it doesn't matter. So let's take this guy here. What is your X double dot? X double dot equals R minus 9X. Let's do the bigger one first. Minus 7X dot, then minus 9X, right? Okay. So you have to add all these three right here. This is the adding junction, right? So what are you going to add? You have going to add R, right? This is R. This guy is done. R, this is R, right? This is R. Then, if you want, you can make a block here, the scaling block, which is simply 1, right? Simply 1. This is your R. This is your RT. Multiply by 1 gives me RT. So is the R plus or minus? Guys, help me here. I want you to help me, please. So it is plus or minus? Plus, right? That's why this guy is plus here. And the other one is minus. This guy is, okay, what comes out RT? What is your goal? Your goal is to this, right? To get this. Your goal is to get this. So get from there you get X double dot. Okay. So this is your output. That's the output you get, right? So what are the input? Your input is this guy, and this guy. These are the input, these are the output, right? This is the output, right? There is only one output, obviously. And there are three things you have to add together to get one. Okay. This is your final answer. You need to add these all to get the final answer. So X double dot is the final answer. Now you have to add all these three now. You already have R is done. Now you have to add X dot. So how do you get X dot from X double dot? Do the integration and you get X dot. You also need X, right? Let's do the one more integration. Then you get X. I don't think you need any more. So then, okay, let's do the addition again. So we have this thing. So you have R done, now X dot. X dot, you have to feed that guy to this guy. Oh, I forgot something here. I forgot the scaling block because my scaling is 7 here. This is 7. See, 7X dot, right? See that? 7X dot. But this is minus. That's why this is minus here. You have to add, point. You have to show minus there. Then you have the X again. So X comes from here, right? So you have the scaling block. Help me here. What is the scaling block? X.
9.
This is 9 then. And this minus or plus here?
Minus.
Minus, okay. So you have two minuses, see? 1, 2 minuses and 1 plus. That's what it is, right? This plus, these two minuses. So when you add them together at the summing junction like this, then you get x double dot out of it. And from x double dot, you integrate, get the x dot. From there, you integrate, get x. Okay. Now x part is done. Now the thing is, what is the other part? The other now you have to represent this guy. Now you have to represent this guy, because this guy x dot. So this guy now. How to represent c? This is my c, right? This is my c. How to represent c? So yeah, your c is here, right? Your c summing junction is here now. This is for the c. C, you get c out of it, okay? You get c out of it. So what do you have to add? You have to add these two guys to get c, right? You have to add x. This guy goes through the one scaling block and goes here. Okay, this is for x. This guy is done, okay? Then you have 2 times x double dot. So what is the, so x dot, what is the x dot? This guy, right? This is x dot. From here, go to the 2 block and add here. Now you have to figure out the sign here. Are these both plus or minus? Or guys, help me here. How did you determine the sign? You get c by adding these two. So both of them are plus, right? So this is plus, this is plus. This is how you generate the block diagram. See, everything can be represented in one diagram. How cool is this? Now you just give me one diagram and I can create the system out of it. I can solve the system rather. Okay, this is guys, question here. If you have question, I'm ready.
What's the difference between the circle with the plus in it and the circle with the x in it?
Oh, it's the same thing.
Oh, okay.
Yeah,
Cool.
that's okay. Yeah, you can do plus also. Yeah, I think in some books they say cross. I don't know. That's okay. It's the same thing. I think books say cross. I don't know. For some reason, I do plus. Okay, now let's go to the next one. So converting state space to the transformation. Now let's go back, meaning going from chapter 3 to chapter 2. That's what I meant. Chapter 3, go back to chapter 3. Sorry, chapter 2.
I'm sorry, Professor. Could you go back for just a second?
Sure.
Thank you. I appreciate it.
All right, no problem. So here, now next thing is we have to convert the state space to the transfer function. State space to the transfer function, meaning we are going from chapter 3 to chapter 2. We can go back to chapter 2 from chapter 3, okay? That's what I'm trying to do. So in chapter 3, what did we have? We just have these two equations. That's the goal of chapter 2, right? That's what we did. We didn't do anything else. We just figured out these two equations. X dot equals ax plus bu. Okay, where u is input. Remember the u is input. And y is output, okay? Y is output. Keep that in mind. Now take the Laplace transform of this guy here. What is the Laplace transform of this guy? SXS. What is the Laplace transform of this guy? AXS. What is the Laplace transform of this guy? BUS. That's what I did. Then from here, what do I get? From here, so from here I get, so what do I get? Help me guys. I'm lost here. SI XS minus AX equals BU. Can I do that? then Si minus A. Why did I put here I? Why can't I simply say S? Because this A is matrix, right? A is matrix. This S is scalar. S is scalar, A is matrix. You are trying to subtract banana from apple. That's not valid. That's illegal. So that's why you have to make all this also matrix, meaning just multiply by identity matrix here. Si minus A equals Bu. So then multiply both sides by inverse of Si minus A on both sides, meaning you have Bu here, right? Si minus 1. Remember, you cannot put this guy here. You cannot put Si here. Okay, because in matrix AB not equal to BA in matrix, right? You cannot do that. So that's why if you are multiplied from the front, from the left, you have to multiply from the left. That's what I did. So this guy is 1. This gives you 1. So you are left with X only. Okay. On the left you have simply X. On the right you have these two guys. These three guys rather. Okay. This guy, these three here. Does it make sense so far?
It does. Can you remind me what
So this guy here is xt. Okay, this can be written as this: x dot t equals ax. Oops, axt plus b. Okay, that's the thing, right? But. So, but the thing is, if you take the Laplace transform, then this little x becomes big X, right? With the S in front. So this A, then this is big X with S, function of S. Then B. Did I answer the question, Nick, or you asked different question?
No, it's pretty much that. So when we say big X, it's implied big X S. Pretty much.
Yeah,
We just But okay, yeah. Just want to double check to make sure.
Well, yeah. Thank you. So we are going from time domain to S domain. Mm-hmm. Okay, this is time domain. This is S domain. But when you move the constant from time to S domain, it doesn't change, right? Constant. This is constant, doesn't change. This is constant, doesn't change. Only the variable change. That's why I didn't put any S or T here, because it's the same. You know, you put S, it doesn't matter. If you put AS or AT, it doesn't matter because they are exactly the same. Okay, that's why I didn't put anything there.
Yep, sounds good.
All right. So I got this equation here. Okay, this is how you go from. Now our goal is to get the transfer function from these two equations. Okay, we are not done yet because we just have X. So what is a transfer function? Transfer function is input over output or input, right? What is output? Output is Y. What is input? Input is U. That's how you define transfer function, right? So you have to get the Laplace transform of this guy, Laplace transform of this guy from these two equations and put it here like this. It means we are going from chapter 3 to chapter 2. Okay. So now, so your X is done, but you need to figure out Y and U. You figure out X here, you figure out X, but you need to figure out Y, okay? How do you figure out Y? By using this guy. So let's put it here. So what is the Laplace transform of this guy now? Big Y equals C big X plus D big U, right? See, this little becomes big here. Everything is big. Then, now plug in the value of X. What is X? X is right here, okay? Plug this in here. What do you get? C is C. So this du is du here. We didn't change it. But how about this guy, this x? This x is this guy here. So that's what I did here. Okay. Now you have us here. You have us here. Then can I take them? Can I factor it out? Because see, remember this u is the factor that multiplies from the right, right? That's why you have to take to the, you have to factor out to the right. You cannot write like that. You cannot write us in the front. You cannot do that, okay? Because this is the matrix. Again, AB is not equal to BA in matrix. That's why I just factor this out and you have US here. Then you have left with D here. How about here? You have C, this guy here. Does it make sense? What is your goal? Your goal is to figure out U over Y, right? Can you get U over Y from here? How do you get U over Y from here? No, other way around. Y over U, because Y is output, right? Sorry. Y S over U, because transfer function is output over input, not input over output. So that's why you need to find Y over U. Y over U, how do you find Y over U? This is Y divided by U, this one. So you got this guy here, which is this. Okay. So if you want to do the transfer function, if you want to find the transfer function, then, so you are given this, right? You are given this. Meaning you are given A, you are given B, you are given C, you are given D, right? See? So you have A, you have B, you have C, you have D. Now, once you have A, B, C, D, then you can figure out transfer function by using this formula. So let's use this formula and do the transfer function. Right, so far so good, or is there any question, confusion?
So far, so good.
Okay, very good. Now, let's do the one problem. So then I think that will clarify everything. So this is given. This is given. You need to figure out Laplace transform of Y divided by Laplace transform of U. U is input, right? U is input and Y is output. So we need to figure out Y. So what is the formula? Now you don't have to do this again and again. You don't have to derive everything here. You don't have to derive, just you can pick this formula now. We already derived it, just you need to add this guy. That's all. Okay, let's use that. So we need this guy here. That's the thing we derived before, right? All right, so then what is C here? Your first goal is to figure out this guy here. First goal is to figure out this guy here, because that's the difficult one. C is already there, B is already there, right? So that's not difficult because it's there. Your, yeah. So what is your B? B is this guy. This is your B, right? This is your B. This is your A. Okay, this is your C, right? And D is 0, right? D is 0. So D is 0. C is this guy. A is this guy. B is this guy. Okay. So only thing you need to figure out is, so C is there. B is there. D is there. Only thing you need to figure out is this guy here. This, that thing in the between. In between. This guy is difficult. I mean, it's not difficult, but you have to do some, works. You have to do some work here. So let's begin with Si minus A. It's finding the inverse of matrix, right? That's the thing. If you have matrix P, then how do you find the inverse of matrix P? That's the thing. Okay. So this is like matrix P now. So your P is this guy here, Si minus A. So what is Si minus A? Si. What is your Si? A is 3 by 3, right? This is your 3 by 3 matrix. This is your A. Since A is 3 by 3, you have to choose 3 by 3 I. 0, 0, 1. But once you multiply this guy by S, right? This guy multiply by S, what do you get? Everything else will be 0. And this guy becomes S, this guy becomes S, this guy becomes S. This is S, this is S, this is S. That's your Si. Our Si is done. Then you have to subtract A from here, this A, this guy. You have to subtract from there. What do you get if you subtract this guy? 0, 1, 0, 0, 0, 1, right? Then what do you have here? Negative 1, negative 2, negative 3. Now what do you get if you subtract this guy? S minus 0, S, 0 minus 1, minus 1, 0 minus 0, 0, 0 minus 0, 0. You got the idea, right? So and you get this matrix here. Okay. Now we have Si minus A finally. But the thing is, that's not that easy. Now the thing is, you have to do the inverse. Remember what is the definition of inverse? Adjunct. What is this ADJ called? Adjoint. ADJ means adjoint, right? Adjoint of matrix, some matrix, right? In our case P over determinant of P. That's how you figure out P inverse, right? So that's my P inverse. That's how you figure out. So the thing is, you have to figure out the adjoint of P and determinant of P. You have to do that one at a time now. So let's do that. So do I have to do this, or you can do it? Can I leave up to you? Simply skip it, or you want me to do it? I can do it if you want me to.
It would be helpful to see how to do it because I don't remember.
Okay, that's fine. So let me do it. So this is your. So my goal is to figure out adjoint Si minus A over determinant Si minus A. That's my Si minus A inverse, right? That's what I'm going to do. Let's figure out this guy first. Something on the top. Numerator. Let's figure out numerator, then we'll do the denominator. So let's see. To do the adjoint, you have to first do the minor. So first we have to do the minor. What is the minor of S? Minor of S is, that's the M1, that's called M11, by the way. Okay, when you find the M minor, you are trying to find M11. Because S is M11, right? This guy is M12. This guy is M13, so on and so forth. We have to find 9 times for each of them. So how do you find M11? M11 is found by this guy here. What is left with? What are left with? You are left with M11 is S minus 1, 2, S plus 2, 3. What is the determinant of this guy? Determinant is S plus 3. Remember this cross? Then when you go up, you got, what do you got? What did you get here? So the minus plus, right? Plus 2. What do you get here? S square plus 3S plus 2. That's what you got. Now your minor M11 is done. Okay. So similarly, what is this guy? What is the M12? M12 is, just cross this out, then what are you left with? 0 minus 1, 1 S plus 3. Then what do you get here? This guy, 0, this is 1, so simply 1, done. What is your M13? M13 is, this is M13, right? So you have 0S, 1, 2. What do you get? Help me here. Negative s, right? Because this is 0, this is negative s. So your 3 components are done. Let's do this guy here. What is the M1, what is the name of this guy? This is 2, 1, right? M21. What is M21? So this guy is gone, this guy is gone. What are you left with? Minus 1, 0, 2 s plus 3. What do you get here? You got this multiplied together, minus s minus 3. Then you got 0 here, right? So that's it. So now how about the other one now? What is this guy? What is the minor of this guy? M22 equals, help me, S0, 1 s plus 3, right? What is the determinant of this guy here? This is 0, so s squared plus 3 s, right? So how about the other one? The thing, this guy. This is M23. What is M23? This is done. Now you are left with 2s plus 1. Can I simply write 2s plus 1 here? Okay. Then similarly, what is the minor of this guy? M31. So you have this guy here. Then what is this? Minus 1, 0, s minus 1. What do you get here? So this is 1, this is 0, simply 1. What is M32? M32 is this guy. What is the minor of this guy? So this is gone, right? S0, 0, negative 1. So what do you get here? Negative s, that's it. Then what is the other? Now finally we have this guy. What is the minor of this guy? M33 equals, you are done with this. So you are left with the s minus 1, 0 s, oops. So what do you get here? S squared. So then how do you find the cofactor? Now first you have to find the cofactor out of it. So what is the cofactor? Cofactor is, put all the minors together here. Put all minors together. That will be your cofactor. What is the M11? M11 goes here. What is M11? Help me here. S squared plus 3s plus 2. That's your M1. So what is your M12? M12 is 1. What is your M13? Minus s. Guys, are you guys with me? Please.
Yeah, I think so.
So then what is this guy here? S squared plus 3s. What is this guy here? 2s plus 1. 2s plus 1. What is here? 1. What is this guy? Minus s. What is s? This is s. S squared. This is not cofactor at, okay? This is not cofactor. What do you have to, how do you find the cofactor? You have just have the minor, okay? It's not cofactor at. So to do the cofactor, you have to multiply by, you have to take the alternate sign here. This is plus, this is minus. This is plus, then this is plus, this is minus. This is plus, this is minus, then plus, right? Then this is minus. Plus, minus, this is plus. Then this is minus. And this is plus. See, I alternate the sign here. Plus, minus, plus, minus, plus, minus, plus, minus, plus, minus. See, I just alternate. Now this is called cofactor. Okay. Now from cofactor you can find the adjoint. How do you find the adjoint out of cofactor? You have to take the transpose. How do you take the transpose? Now the cofactor is, sorry, this implies adjoint now. Adjoint is transpose of cofactor. So meaning this guy goes to the column like this. So meaning so s squared plus 3s plus 2, then minus 1 minus s. This guy goes to the column. Make sense? Then this guy goes to the next column. What is here? This minus minus plus, this minus minus plus. Can I simply write s plus 3? Then here, s square plus 3s. S square plus 3s. Then here, minus 2s plus 1. That's your, now you finally have this one. 1, then plus s, then s square. Finally, you got this one. You got the adjoint. Now you have to find the determinant. You know how to do that, right? I hope you can do that. Find the determinant of that guy. So I'll give you the answer now. So now you have, see, you have the determinant here. Sorry, this is the adjoint, right? You got the same, exact same adjoint. Now, if you do the determinant of this guy, right? If you do the determinant of this guy, then you get this, you get this one here. So then this is your, now you have your this guy now, you have this guy. Now that finally you have to add, you have to put this in here. Now this guy goes in here, then C, so write this like this now. You have C times, okay, let me do it nicely, okay? So you have C, plug this in here, which is this is C. Then you got this one already, right? Then B, then you have D. So you just multiply them together. Then you end up, you end up getting this guy. Okay. With this, I conclude this chapter 3 and go to chapter 4. So this, until chapter 3, we just formulated the problem. Now we want to solve the problem now. Okay, that's what we'll be doing in this chapter. But before I do that, I want to introduce some basic concept. So we'll talk about time response, system time response. So I'll take you guys to chapter 1 now. So remember we talked about steady state and transient response. So there are two kinds of response, right? Time response. Now, time response. There are two kinds of response. So what are they? If you help me here in chapter 1, steady state, right? I missed. Yes, steady state. And the other one is transient, right? Transient response. Steady state response and transient response. This is how you, this is how you see there are two kinds of time response. But there is another way of seeing time response too. So there are two kinds of time response, but in different ways. So you can say forced response. So I'll ask somebody who has already taken DFQ. And what is the other one? Free response, right? Have you guys done this in the differential equation?
Yes, we looked at it a little bit.
Yeah. So if I rename this guy, you might click, particular solution. Remember particular solution?
Oh yeah.
And complementary solution.
Yeah.
So that's what it is. So it depends on how you see the problem, right? Sometimes you see there are two kinds of response, steady state and transient response. Sometimes you view this in this way. It's the way you see the problem, okay? Just like noun, okay? How many kinds of nouns are there? There are two kinds of noun, countable, uncountable. Uncountable, right? Uncountable. But there is other way that we can categorize noun also, you know, common noun, proper noun, blah, 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 right? So there are different perspectives, right? This is one perspective, this is another perspective. In the same way, time response also you have different name here. So you have steady state, transient, or, you know, particular, complementary, this kind of stuff. Okay. So then what is the, once you have, suppose you have, now how do you get the total? This is so bright dark, sorry, red. So let me choose different color. So time, what is the total output, total response? From here, what is the total response? If you use this, then what is the total response? Total response YT equals steady state. This is steady state, okay? Steady state. Then what is the other one? Plus transient, right? Transient, we can say tilde, Y tilde. So this is transient. So your total solution is YT equals, you have to add all together. You have to both together. There are just two of them, right? So what happens if the time is so big? If the time is so big, right? If the time gets bigger, then what happens? The transient response becomes 0, right? If you recall your chapter 1, if you recall your chapter 1, at one time is infinity, not 0. When time is very big, then this guy is 0. Then your total solution is YT equals simply Y bar. This is one way of looking at the time response. Then other way is obviously, as I said, is the forced, right? So you can say particular versus complementary, or you can say steady state. So this force has different names here. See that? So forced response has another name, which is steady state response or particular solution, or and the natural, and the other one, complementary response, has different names too. You can say free response, you can say homogeneous solution, or you can say natural response. It has different name. But in this case, what is the total response? Total response YT equals YH plus P. H for homogeneous, P for particular. So you add them together, then you get the total output response. But what is homogeneous solution? What is this guy? This guy is the response obtained without with zero input. Without input, what is the response of the system? So there is no input at. Without input, what is the response? That's your YH. Okay. Then what is particular solution? What is this guy? Particular solution, the response obtained with the input into it. Okay. That's the thing. Now, before I go to the real solution of the problem, then before I reach there, let me introduce some important concepts, some other concepts. So here I'm going to introduce poles, zeros, pole sign zeros. Okay, these are very, very important concepts. So we'll be using this a lot now. Okay, we have to use this again and again and again. So this is very important response. So I want you guys to understand clearly. Okay. Again, to understand poles, I will start with the transfer function. Okay. What is the transfer function? How do you write transfer function? Transfer function GS equals output over input, right? Remember? Output over input. That's the transfer function, right? So how do you represent? Yeah. So this Y is numerator, right? D is denominator. Okay. So when you equate this n equals 0, what is the value of s you get? These are called poles. So when you equate denominator to 0, what is the value of s you get? That's called poles. Zeros, poles. When you set the denominator equals 0, the values of s you get are called poles. When you equate numerator equals 0, values of s you get are called zeros. So zeros are represented in the graph like 0, simply 0. See, make a 0 for the 0. For the poles, you have to put the cross mark like this. That's how you represent it in graph. Let me show you how. Okay. Oops. Suppose you are given a transfer function like this, right? This is your transfer function. This is your transfer function where a and b both are positive. Okay. A is positive, let's say 3. B is positive, let's say 5. I don't know. Not negative. Okay. Not negative. Both of them are positive. So it's like a plus 5, s plus 5, s plus 5, s plus 3. So 5 is b, 3 is a. That's what I meant. Then if you equate, let me simply write b for now. Okay. B and a. B and a. So if we equate this guy to 0, what is the value of s from here? Negative b. That's your 0. That's your 0. If you equate this guy to 0, what do you get? S equals minus a. That's your pole. So how do you represent this in the s space? See, you have two s here. S equals minus 1, minus a, s equals minus b. How do you represent that in the s domain? So what is s domain? S domain, it has s equals sigma plus j omega. Okay, sigma is the real part, omega is the imaginary part. So that's why I have sigma here, I have j omega here. So you have two s here. Okay, s equals minus a. Minus a can be written as minus a plus j times 0. Minus b plus j times 0, right? So that's why, meaning this guy stay on the x-axis. Okay, so because this is your y-axis, this is your x-axis, right? You don't have the imaginary part. Thus you have the real part only, because remember you have a and b, both of them are real. That's why when you plot on this plane, then you have a. So remember a is greater than b, right? A is greater than b. So that's why this is a, right? This is a, this is b. So a is longer than b, but they are in the negative direction, negative axis. That's why we represent like that. So guys, do you understand what the pole is and what the 0 is?
Can you explain again why what you mean by real versus imaginary in respects to omega and sigma?
So s is equal to sigma plus j omega. Okay, that's the s space. Remember we have been talking about s all the time in Laplace transform, right? Laplace transform is s domain.
Yep. Yep.
So this s has two parts. One, the real part, which is sigma. The other part is imaginary part, which is omega. Okay, complex number has two parts. Complex number has real parts and imaginary part. simply say, yeah, we simply say Im and Re. Real part is sigma, imaginary part is omega. Now we have poles S equals minus A and S equals minus B, right? It means what is the imaginary part? It's not there, meaning it's zero. It's zero. So that means when you plot this guy on this real versus imaginary axis, right, like this is real, this is imaginary, then this S goes to just real axis only because your imaginary part is zero. That's why you have to do on the real axis only. Make sense? So then how do you plot this guy? So A, this is your A, this is your A, and this is your B. But they are negative, right? That's why you have in the negative axis here. This is negative A, this is negative B. This is how you plot on S plane. This is called S plane, by the way. Did I answer your question, Nick?
Yeah, I guess I just don't. I don't understand the concept of why we're calling them the real and imaginary axes. Is that just a term that we use just because, or is that specific to time response stuff?
Okay.
Or is it super important? It's just what we call them.
So I have to go from here. So we know what S is, right?
Yeah.
So S is the parameter in S space. Like if you have x dot t, if you take the Laplace transform, right, you got S times xs, right? So what is this S? This S is actually, the definition of S is sigma plus j omega.
Mm-hmm.
Okay, so your S is, this is sigma plus j omega. J omega is 0. So this S equals sigma plus j omega. Omega is 0. There's nothing means it's 0, right? So now I can plot, this is like x plus y now, okay? This is like x plus y. Real part is x part, and this part is y part now. The way we plot in the xy axis, remember? Xy axis, we can plot the complex number also in the same way. So this is complex number, we plot this x-axis is sigma and this y-axis is j omega. That's what you do.
Gotcha.
Okay? Yeah.
Okay.
All right. All right, let's figure out the pole of a particular problem, because we didn't put the number, right? We just put A and B, right? So let's put a particular number for A and B. My transfer function is z equals s plus 2 divided by s plus 5. So what is the pole here? Help me. What is the pole? Denominator equals 0, right? Pole we get by equating this guy to 0. So what do you get? S equals negative 5. That's your pole. How about the 0? Equate that to 0, you get s equals negative 2. That's your 0. 0 is s equals minus 2. Pole is s equals minus 5. Okay? Does it make sense? Now, what I'm going to do here is, I'm given G, right? I'm given G. So, I'm given G. This G is given. Now, I need to find C. For that, I need input, right? Your G is given. Your G equals C over R, right? R is, yeah, C is output. R is input. Now, G is given. Then how do we find output? C equals G times R, right? So G is given. Now to find C, you need to have R also. Does it make sense? To find C, you need to have R also, not only G. What is R then? What is R? Okay. The easiest one is 1 over S. Easiest R is 1 over S. So the simplest one, I would say. Okay. Then what is your C then? G is S plus 2 divided by S plus 5. That's the G. Then R is 1 over S, right? So you can simply write S here because 1 over S, 1 multiplied this. So you have this one now. This is your C. Guys, question here so far?
So that so R equals 1 over S, that's like given to us?
Yes.
Okay, thanks.
Yeah, it's given to us. But if you want to test it, right? Suppose you are an engineer, right? You are an engineer. So you found the transfer function. Now you are a test whether this is useful to you or not, right? Okay, you are to test it. Okay, whether this guy is useful or not. Then you have to choose some. You have to get the output, right? From G you get the output because G equals C over R. Since you know G, you get C by multiplying G with R. So you already have G. You want to test your G whether this is useful or not. So to test that, you pick some very simple R. Why do you choose the complex one, right? Because you are just testing. So the testing R is that you just want to test by using 1 over S. You know what 1 over S is? This is your 1 over S. Meaning before you it's like, so this is the time you started doing it, okay? Before the time there is no input. After this time you have constant input, or your input does not vary. Okay, let's say this is the object. Okay, at t equals 0, your force is 0. Okay, right at t equals 0, you started applying force equals, let's say this is the force you applied to this guy. Let's say 3 Newton force, right? Okay, then for t greater than 0, your force is 3 all the time throughout. You are applying constant force all the time to move the body. Before that time, the force was, there is no force. No force before this. After this, you have constant force. This kind of response is called 1 over S. So in the time domain, we call it step function. In time domain, we call it step function. In the S domain, we call it 1 over S. Remember, the Laplace transform of U is what? 1 over S. That's what it is. Okay. Now what you have to do here is do the partial fraction, right? So do the partial fraction. So you got C equals, let me do it here. C equals, CS equals A over S, because you have 2 factors here on the denominator, right? So S and B over S plus 5. So how do you find the partial fraction? Your CS is given, right? Your CS is S plus 2 divided by S plus 5. Then what do you have on the right? S plus 5 on the denominator. Then you have A times S plus 5 plus B times S. Then this guy cancel out. Then you are left with S plus 2 equals A times S plus 5 plus BS. Now you have this. How do you determine A and B? How do you determine this here A and B from here? When S equals 0, what do you get? This guy is 0, right? This guy is 0. Then 2 equals A times 5. So what do you get? A equals 2 over 5. See that? That's what I have. A equals 2 over 5. Similarly, you get B equals 3 over 5. If you do the same thing again, S equals minus 5, right? If you put S equals minus 5, then you get 3/2 here. So this is how you do the partial fraction, right? Okay. Now take the inverse Laplace transform now. See, chapter 3 stays here. Chapter 3 stays here. This is chapter 3. Chapter 1 and 2 and 3. Then in chapter 4, we add RS and we have CS here. Then we have the partial fraction. Now you take the inverse Laplace transform here. Take the inverse Laplace transform. Inverse Laplace transform. So what do you get? What is inverse Laplace transform of C? CS is CT, right? What is inverse Laplace transform of this guy? This guy can be written as 2/5, 1/s. So 2/5 is 2/5. 1/, what is the inverse Laplace transform of 1/s? Simply 1. Then 3/5 is 3/5. Then what is the Laplace transform of this guy here? 1/s plus 5. E to the negative 5t. Does it make sense so far? Okay, now I have this guy here. I have your output is this. So, and you have this guy's output. This is output in. So can I write this guy as this? S minus 0. This is S. Okay, what is this?
According to Merriam-Webster,
Sorry.
used to indicate the person,
Sorry.
thing, or idea that.
No. So what is this system? What is this pipe in the axis, right? Like this. What is this 5? -5, right? This is the pole. Why am I doing like this? This is Y, this is x-axis, right? So how do you plot this guy? So this guy S, the pole from here. What is the pole from here? -5, right here somewhere, right? This is -5. This is sigma. This is j omega, right? So similarly, see, we did the pole of the system, right? This is the pole of the system. Where does this S plus 5 coming from? S plus 5 is coming from GS, right? GS is system. Okay, that's why this 5 is called pole of the system. Then similarly, where does this come from? So if you equate these two, S minus 0 equals 0, what do you get? S equals 0. This is also a pole. Where does this pole come from? Where did this come from? This pole came from input, not from the system. So this is the input. So I will call this the input pole. Input pole. And I call this system pole. There are two poles now. System pole is right here. Input pole is right here. Guys, so I think we don't have any more time left, right? So any questions so far? So we have two poles here, okay? That's what I conclude now. One from the system and other from the input.